Okay, so yesterday we were doing the non-relativistic limit of the Dirac equation. And we had introduced actually the Dirac equation coupled to an electromagnetic field indicated, and we call this pi mu. Okay, and then the Dirac equation, I will not work out the details, otherwise I have to repeat, became the following one. We use a 2 by 2 component notation. Okay, so this is the 4 Dirac Spinors that we wrote as 2 component, 2 upper component, 2 lower component. And this is the full Dirac equation once you write it with coupling to an electromagnetic field. The electromagnetic field appears here and there. And then we factor out the mass. So we have phi tilde, chi tilde. We decided to write yesterday in this manner: exponential minus I m0 c square over h t, so that somehow this carry the kinetic energy, and the mass part we have already factored out. Then using the phi and chi instead of the phi tilde, chi tilde, this equation becomes, yes? What did you say? Where? Which one? This one? Pi. I cannot. The first line. This is C, and this is E. Above here, this is sigma, the Pauli matrices, okay? The Pauli matrices, sorry for my handwriting. Now, if we want to find, if we insert this into that, we get an equation for phi and chi, and the equation is the following thing. But the things that happen is that here now there is a 0, and here there is a minus 2 plus chi, okay? Now, as this object here carries only the kinetic energy, and we are in the non-relativistic limit, we can assume that d chi dt, that is basically the energy, is much less than the mass energy, the energy carried by the mass of the particle, and the same for the potential energy, A0 chi. There isn't a manner to turn on the air conditioning? There, I think. Turn it on, because it's getting very hot, and it will get very hot. Okay, so both the kinetic energy and the potential energy carried but as in the non-relativistic limit are very small. So in the lower component, here, in the lower component of this equation, we can neglect this part because it's very small, and we can neglect this part because it's very small. And first things, Let me see. Okay, and so in the lower component, if we neglect that, we will get only these two pieces. So we neglect this because it's much smaller than the mass, so we neglect this, and we are left only with this part and this part. Sorry, we neglect this, the potential energy and the kinetic energy that is small of the lower component because we have this. So for the lower component, we get only this equation, C sigma dot pi phi minus 2m0 c square chi equals 0. And from here we get chi equal sigma dot pi 2m0 c square, no, c phi. Okay. Now, if we insert in the upper component now, let's insert in the upper component, replacing everywhere chi with that expression, what we will get is I h d dt phi equal sigma dot pi over 2m0 phi plus E A0 phi. Okay, so basically in the non-relativistic limit, we have reduced the Dirac four-dimensional equation to a two-dimensional equation because this object has two components only. Okay? Now let's remember another thing. Let's remember that when we have that famous formula that tells us that when you have the scalar product between the sigma matrix of Pauli and the vector, then there is a formula that we used yesterday heavily, and let me write it here for this case, is sigma dot p dot pi sigma dot pi is equal to pi square plus I sigma pi wedge pi. Now this is not 0 because pi is an operator, so this wedge product is not 0. You have to work it out what it becomes, but we can do it here. So let's use here that formula there, and what we get is that this object sigma dot pi, remembering that is an operator because this is a derivative, okay, with respect to x mu. This one, okay, is equal to pi square plus I sigma pi wedge pi. Then this object become pi minus ECA square plus I sigma, and now I have this wedge product, and this wedge product is 1 over h okay, you see now why it is not 0, because you know when you do the this is not just a vector, it's an operator, and so even if you do the wedge product, it's not 0. It's 0 if it were two vectors, but they are operators, so you have to make it act on the left and on the right, and what you get is P minus E C A square minus, do this, and then you get the rotor of A, that is the electromagnetic, the magnetic field, and the net result, we will not work out all the things, but is sigma dot B, where B is the magnetic field. Okay, so now this expression that entered there, we replace with this one. Let me cancel here now. Yes? No, the lower component. Yes. I don't understand. Yes. That instead of using the lower component, we use the upper component, we would get something equal to 0. But you know, usually, if you remember the non-relativistic limit in the we said that is the lower component that is the small component. If you remember what we did with the Klein-Gordon. So that is why we apply this to the lower component. Okay, and go on to work with the lower component. And once you insert in the full Dirac equation that I canceled, this, you get this equation for the things. So okay, so now this equation, we replace into this equation this expression, and what we get is the following things. IH d phi dt equal P minus ECA squared 2m0 minus EH 2m0C sigma dot B plus EA0 phi. Okay. Now, so this is the non-relativistic version of the Dirac equation in interaction with an electromagnetic field. And you see, it is a charged particle. What the result we get is a charged particle, but that we knew we put in a charged particle in order to interact with the electromagnetic field. But what we got out of the Dirac equation is this interaction. And this interaction is a very interesting one because this is what is called the magnetic moment, the Bohr magnetic magneton, sorry, this quantity, and multiplied by sigma, you get nothing else than the magnetic moment. So you have the interaction of a magnetic moment with B and the magnetic moment carried by a particle with spin 1/2. So this is where you get the information that you are working with a spin 1/2 particle. Okay, this interaction really come, well, we could have done non-relativistically. That means if non-relativistically we want the I know that you have not done the Pauli equation. This is the Pauli equation. We will work out a little bit more in detail. The Pauli equation is the interaction. It tells you how a particle of spin 1/2 interact with an electromagnetic field. And well, if it is a spin 1/2, you need a two-component object. And in fact, this is a two-component object. Then you have the usual kinetic term. But if this two-component object has a spin, then, and it has a charge, then it carries a magnetic moment that is this. And this magnetic moment, we know that magnetic moment interacts with, you have learned from electromagnetism, the magnetic moment interact with magnetic field in this manner. And this is exactly the interaction. But from here, having a sigma Pauli matrix, we read that this is a spin 1/2 particle. So that is where, in doing the non-relativistic limit, we gather the information that the original particle of Dirac was a spin 1/2 particle, because the interaction we get is typical of a spin 1/2 particle with a magnetic field. This is what is called Pauli equation. And of course, it was not derived from the Dirac. Pauli derived it before, just after the Schrödinger equation. He asked himself how a spin 1/2 particle interact, and he got these things. Okay, now let's do one more thing. When there is the interaction of a magnetic a spin 1/2 particle, you know, the particle not only has a spin that creates a magnetic moment, but it has also, the particle is moving, so it can have an angular momentum. And then the angular momentum generates also magnetic moment. So there are two magnetic moments, one generated by the angular momentum of the particle and the other generated by the spin. So from here, having got this, for sure now we know that this is an equation for a spin 1/2. And then it means also the Dirac was a particle for, things for a spin 1/2 particle. And why instead of having two components in the Dirac we have four? Because you know, two components, these two components are due to the spin. The other two are due to the fact that you have positive and negative energy. That is why you double and you have four. So the Pauli equation, that is the non-relativistic, has only two components and is due to the spin. Why the Dirac, so this is the Pauli. Why the Dirac has four? The Dirac has four because two are due to the spin, and the other two are due to the fact that you have positive and negative energy, so this gets doubled with these things. But first of all, there was another important issue, that the interaction of the magnetic field for the spin part somehow was not of this form, but that means if you introduce 1/2 h bar sigma, the spin operator, then it was not this quantity is the magnetic moment times S times B, but somehow you had to put here a 2. This 2 is called gyromagnetic moment, gyromagnetic ratio, gyromagnetic ratio. And nobody understood why it was 2. They call it anomalous and so on and so forth. For the spin, it was this 2. Now we understand this quantity that is exactly this is this. So the gyromagnetic ratio or coefficient for spin 1/2 particle is 2. And the reason is, now we have done a derivation from the Dirac equation. There we did not postulate any gyromagnetic factor or anything. We just did the non-relativistic limit and we got the right factor of 2, because this object that is equal to this can be written in this manner, where this is the magnetic, this is the magneton, the Bohr magneton. But let's see the difference between the interaction of a spin and the interaction of an angular momentum. So that means if we have an angular momentum of a charged particle, then we have a magnetic moment, but then we have also the intrinsic magnetic moment due to the spin, because the spin is like a small magnet. Okay, so the spin, don't visualize, I don't know how you were taught quantum mechanics, but don't visualize the spin as the particle is rotating. The particle is point-like, the electron, even at the present energy, is point-like, and so it does not rotate on itself. The spin is basically the indication that the magnetic, that the particle, the electron, carries a magnetic moment, okay? And in fact, the Stern-Gerlach experiment did not detect that the spin, that the particle is rotating, but it detected that there is a deviation. Remember the Stern-Gerlach experiment, it detected there was two magnets. And here there was a magnetic field, but that had a gradient, and then they saw that the two beams split. And so basically they did not detect that it rotates. They detected that the particle carries a magnetic moment. It's like a small magnet, okay? Remember this, because many from the word spin, they think it is spinning. Nobody has ever seen the spinning of the electron. What they have seen is the magnetic effect. But anyhow, let's do the following things. As you know that B is rho of A, let's take now a constant magnetic field, a uniform magnetic field. Then we can choose as A, so B uniform means constant. Then A can be written in the following manner: B wedge X. And then let's see, here we have factored out the spin part. Let's work out this part. P minus E C A square, then is P minus E over 2C B wedge X square. And if you work this out, you get roughly, if you neglect term that are order C square, 1 over C square, you get P minus E C B wedge X times P, and this is equal to P square minus E square C B times the angular momentum, where L is the angular momentum, X wedge P. Okay, so if you now insert it here, we have worked out the kinetic piece and made the magnetic moment appear. Then we get d phi dt equal P square over 2m0 minus E over 2m0 C. And then you have the angular momentum plus this part is 2s, where s is the spin, so 1/2 times sigma times B plus E A0 phi. Okay, and you see the coefficient in front of L is 1, the coefficient in front of the spin is 2. This factor of 2 comes exactly from the Dirac equation. So if somebody asks you, can you tell me where the geomagnetic anomalous factor of 2 for the spin in interaction with the magnetic field come from? The only answer is it comes from the Dirac equation, okay? Because this was derived from the Dirac equation, and if you work out all the things, it produces a factor of 2. Okay. So the important fact about the non-relativistic limit is it tells me that the particle involved is a spin 1/2 particle, because I get exactly the Pauli equation, that is a two-component equation. Second, it tells me that the geomagnetic factor for the spin, why the geomagnetic factor of the spin is 2. Please, it is everything on the book, I'm just copying, okay? Don't need to take any notes on this. I mean, just following verbatim the book. Now, okay, what we do now is we will go and we'll start a long chapter on the relativistic covariance of the Dirac equation. You remember when we had the Klein-Gordon equation, it was easy to see that it was relativistic invariant. Okay, so now, yes? Oh, this factor of 2 just is a factor that is in front there, so that means the strength of the interaction, if you use the spin, between the spin and the magnetic things is doubled, so there is a factor of 2 in front. Somehow it is like if instead of the S, it were the sigma that interacted with the magnetic field. It's the same thing, but you know, the analog of the angular momentum is the spin. The spin is 1/2 h bar sigma and so on. Okay, so now let's look at the Lorentz invariance. Of the Dirac equation. You know, in the Klein-Gordon case, we had 1 over, it was second order, so we had this operator. And this operator is clearly Lorentz invariant. Why is clearly Lorentz invariant? Because, you know, this is nothing else than the derivative. I mean, there was an object we knew in that was basically ct square minus x square minus y square minus z square. This is the invariant distance, and we know that this is left invariant by a Lorentz transformation that we did already at the beginning. So this one that is the derivative is the analog of the level of derivative of this. It just transforms in a different manner with the contravariant things, but also this object is invariant, is relativistic invariant. Now, what about the Dirac case? In the Dirac case, we did not have anything that resembles this quantity or this quantity. We had something like alpha I ddxi plus beta plus, well, yeah, if you want, we had ddt plus alpha I ddxi, and then we had the mass term. But this one does not resemble any quadratic piece that are invariant under the Lorentz transformation. So we have to look carefully into it and see what happened. So now we have to look if also the Dirac equation, of which we only know the commutation relation between the alpha is Lorentz invariant or not, or if we have to impose some condition on that to be Lorentz invariant. Now, let's indicate the Lorentz transformation in this manner. So this is a 4×4 matrix. These are 4 vectors that are the usual x, and we transform them in this manner. The index that are crossed, it means with the Einstein convention that they are summed. Now, if we take an infinitesimal distance like dx mu, we know that the infinitesimal distance is invariant under Lorentz transformation, because the Lorentz transformation is nothing else than a generalization of the rotation in 4 dimensions, but what it keeps invariant is this strange object with the minus sign. Okay, so this is a 4 distance. Let's call this d mu, d square, something like that. This is a 4 distance, but it has this feature of having these minus things. But the Lorentz transformation keep that things invariant. So if we do a Lorentz transformation and go to new variable, also the infinitesimal one will be left invariant. Okay, but what does this imply for these matrices? We knew already this, that the Lorentz transformation makes, and the Lorentz, I mean the rotation part plus the boost part, the transformation according the change of frame with the velocity. Let's see what this is. So this is the distance, this is the infinitesimal distance, and when we do a Lorentz transformation, is invariant. Let's see what this implies. Okay, let's take this object, and this object is a mu nu dx nu, a mu sigma dx sigma, and this is equal a mu nu, a mu sigma dx nu dx sigma. And we know that this object is equal to this, so that object is equal to dx mu. But this, what does it imply? It implies that a mu nu, a mu sigma is equal to delta nu sigma. Okay, in order for me, so what did I do? I took the infinitesimal distance. The infinitesimal distance is this. I want to prove, because not I want to prove, I know that the infinitesimal distance does not change if I go to a new frame transformed by a Lorentz transformation where a mu nu are Lorentz transformation. So I inserted here, this one is this, and this one is this, okay? If you do, and you want that all these, what you get is this object, then you have to produce from here a Dirac delta, not a Dirac delta, a Kronecker delta, such that this object becomes exactly that one. Okay, so this is the relation we derive for those matrices A mu nu to mu nu mu sigma to be Lorentz transformation. They have to satisfy this relation, and this is a very important relation because they are called orthonormality relation or orthogonality relation among the coefficient of the Lorentz transformation. And if I ask you where do they come from, that relation, for example, if one of the questions of the written exam is where do these orthogonality relation among the coefficient of the Lorentz transformation come from? They come from the invariance of the infinitesimal distance. Okay, so we can cancel these now, showing how we have derived it. And let's write down here the relation. Well, actually, we better keep the relation here so that there is a set of relation I will keep using. A mu nu A mu sigma equal delta nu sigma. Now, another things that we can do is the following. We can take the determinant of that relation. Let's take the determinant on the left and on the right. Then what we get that the determinant A mu nu A mu sigma is equal to this, but this is 1. So this is another thing that we get. Then we get determinant A mu sigma, because the determinant of a product of two matrices is the product of the two determinants, is equal to 1. But this means the determinant of A mu nu square, it doesn't matter, here I put the element, but you know, there should not be the element. It means take this matrix, and do the determinant. So the determinant of A is equal 1. It means the determinant of A mu nu is equal to plus or minus 1. So let's write them here. The determinant of A mu nu is equal to plus or minus 1. Now, imagine these are Lorentz transformations. So let's imagine we start from the identity. So x mu is equal x mu, and then we slowly change so that we move and we end up in a x mu, in a new x mu, doing a Lorentz transformation. Well, if we move continuously in doing this Lorentz transformation, imagine the Lorentz transformation is like a 4 rotation. But we start from the identity. The identity has determinant 1. The transformation is 1, 1, 1, so the determinant is 1. The determinant cannot change if we smoothly start from that. So how can it be that is equal to minus 1? Well, you can start from this one. You can start from a transformation where xi goes into minus xi. This is also a Lorentz transformation because, you know, the only feature of the Lorentz transformation is that it preserves the distance. So if you send x in minus x, y in minus y, z in minus z, you still get, and also x0 into minus x0, you still get an invariant things and an invariant distance. So these, even with all 4 of them, is just that if I do only on the spatial part, then the determinant of the transformation is equal to minus 1, right? And then if I do a continuous Lorentz transformation, so first transformation I do is a reflection of the coordinates. And then I do continuously a Lorentz transformation. The determinant, as I move continuously, will not jump to -1. It will, it is either 1 or -1. So as I move continuously, there is no parameter that changes this continuously. That means it will remain to -1. So the case -1 corresponds to reflection. So you have a Lorentz reflection in xi in an odd number of x mu. Let's put in this manner. If I do an odd number of reflection in x mu, that means I could change, for example, x0 going into minus x0, and then x1, and then x2, but do nothing on x3, then the overall is -1. Okay, the determinant overall is -1. So -1 is a reflection in an odd number of x mu plus Lorentz transformation. The +1 is reflection in an even number of x mu plus Lorentz transformation. And even number, it could be also 0, that I don't do any reflection. Okay, now you understand why these give me determinant -1, because the A mu nu associated to this is -1, -1, -1 plus 1. And this has determinant -1. Okay, so if I look at this as a Lorentz transformation, and it is a Lorentz transformation because it leaves invariant the distance. So the only feature, remember, the only feature of the Lorentz transformation, it has to leave invariant the 4 distances. Now, those who have determinant -1 are called improper Lorentz transformation, while those that have determinant 1 are called proper Lorentz transformation. Okay. Now, before going into now the detail of the Dirac equation, so this is a general things of the Lorentz transformation, we will indicate with this A mu nu. It includes the normal rotation, but also, and the normal rotation are Aij, where this is a special part and it is only a rotation, but there are also the 0i, and the 0i are the Lorentz boost. Okay. All these transformations have this feature that they preserve the 4 distance. Now let's go back to the Dirac equation, because that was our goal. Our goal today and tomorrow is to understand better the Lorentz structure of the Dirac equation. Okay. We will introduce, we did already yesterday, but let's introduce so let me write it here, that one, x prime mu is equal A mu nu x nu. Let's write now what are called the gamma matrices. If we start with the normal, let's start with the normal Dirac equation. Now let's multiply these on the left by beta over c. If you do, you get the following things: beta IH derivative with respect to CT plus beta alpha I IH dxi psi minus M0, we multiply by B, so C psi equal 0. Now, we have used the fact that beta square is the identity. We have multiplied by beta over c. One c disappears from here. Beta square gives me the identity. So we have this object. Now let's use the following other matrices. I don't like to have products here. Let's use the following other matrix. Gamma 0 equal beta and gamma I equal beta alpha I. Then this equation can be written in a much more compact form, that is the following. IH is factored out from everywhere, okay? And I have gamma 0 ddx0 plus gamma 1 ddx1 plus gamma 2 ddx2 plus gamma 3 ddx3 psi minus m0c psi equals 0. So you see it is much more uniform, and besides it can be written also in a more compact way. This one can be written as I h bar gamma mu ddx mu psi equal m0 c psi. You see, this is a very compact form and the one most used for the Dirac equation using the gamma matrices. Now let's look some of the features of the gamma matrices, because there are features that are extremely important for us. Okay, so is it clear? This is the definition of gamma matrices. Now let's go and look how they are and so on. Okay, let me cancel here. From this fact, immediately you see that gamma 0 is like beta, so it is I 0, 0 minus I, the identity, while gamma I is beta, that is this, multiplied by alpha I, and alpha I, if you remember, was sigma sigma, so basically this one switch the sigma, and you get 0 sigma I minus sigma I 0. Okay, so this is the form in terms of Pauli matrices and identity two-dimensional operator of the gamma matrices. Well, they have a lot of nice feature. Remember that the alpha and beta were Hermitian. Well, the gamma are not Hermitian. For example, well, gamma 0 daga is beta daga, but this is beta and this gamma 0. So the gamma 0 is Hermitian. Let's now look for the gamma I, if it is Hermitian. The gamma I daga, remember, was beta alpha I daga. This is alpha I daga, beta daga. These were Hermitian, so alpha I, beta, but they were also anti-commuting, so they are equal to beta alpha I, and this is minus gamma I. So the gamma I are not Hermitian, at least in this formulation. What else can I say? Okay. The gamma 0 is also unitary, because gamma 0 is equal to gamma 0 daga, okay? But we know that gamma 0 square is beta square, and this is 1. So from these two, basically, this you can write as gamma 0 daga equal 1. So it means that gamma 0 daga acts like the inverse, so gamma 0 is unitary. So there is a lot of nice things that are easy to see. But the most important is the following one. So let me write here the Dirac equation, IH gamma mu d psi dx mu equal m0 c psi. Now, You remember that we had the various okay, just, yeah, maybe what we can do is let's see why it has this form. So let's see why the gamma I has this form. Okay, and this is easy. So gamma I was defined as beta alpha I. Then we have I 0, 0 minus I, and alpha I at this form, sigma I, 0, 0. If you multiply 2 by 2, what you get is 0 sigma I minus sigma I 0. So the gamma I with respect to the alpha I have the sigma in the same position but with opposite sign. And that is also why they are not... now, you remember the various form of the alpha I, alpha j plus alpha j, alpha I was 2 delta ij, alpha I beta plus beta alpha I was 0. Okay, now from this one we can derive which are the commutation relation between the gamma mu. And the commutation relation between the gamma mu is the following one. Gamma mu, so starting from this is homework. Okay, so we cancel the last one, but this is an homework. From this one, derive the following. Gamma mu plus gamma mu is equal to 2g mu nu times the four-dimensional identity, sorry. So this is the anti-commutation relation. You see that if mu and nu are different one from the other, they anti-commute. If they are ij, where the g mu nu that I'm using is this one, 0 minus 1, 1 minus 1 minus 1, and all the rest 0. Okay. So the homework is start from the anti-commutation relation of the alpha I and derive the anti-commutation relation for the G. Okay, I've written down already. You have just to be a little bit patient and see that they get organized in this. And you see, while the alpha, the I, and the beta were not covariant because the one with index 0 we indicated as beta and the one with index I we indicated with alpha I. These are really covariant. This expression is covariant in the sense that you see on the right-hand side you have a tensor, a well-known tensor that is G mu nu. So this expression is covariant while this one, the covariance of this one was not really explicit or manifest. Another piece of notation that I want to give to you is the following. If you have a vector, and imagine that that vector you multiply, suppose you have a vector, mu, and now we do mu, sorry, a vector mu, and we do mu gamma mu. So each matrix gamma mu is multiplied by a number, so this is basically A0 gamma 0 plus gamma I, AI, sorry, so A1 gamma 1 plus A2 gamma 2 plus A3 gamma 3. Okay, this quantity is indicated in this manner, the two indexes are summed, but instead of carrying on all these things, Feynman invented a notation that is this slash. So this object, when you see mu slash, it means mu gamma mu. Okay, this was invented by Feynman, and is a notation that since then has being used. Okay. So this is the homework. Start from this. And of course, you have to use also the fact that beta square is 1, okay? And from here you derive what is alpha square. Alpha square is also 1 and so on. And then you can derive this general expression that is really very important, and we will keep using it continuously. Now, let's go back to our original goal. All this was just formalism. And can I cancel here? Okay, our original goal was written there, the Lorentz covariance of the, so that means we have a frame, this frame is this, and let's do a rotation plus a boost, and we go into another frame that has these and has new coordinates. Now here the Dirac equation was I, H, gamma mu, ddx mu, minus mc applied to psi of x equals 0. This is the equation. And we want to go into an equation that maintains the same form. When we say covariant, it means it maintains the same form. I, H, gamma mu prime, ddx mu, minus m0 c, psi prime of x prime equals 0. You see, it has the same form. Now, why we want that an equation has the same form? Because, you know, if it has the same form, modulo we transform the coordinates, the solutions are the same. And that is clearly what must happen. That means if there is an invariance, if the system has this as a symmetry, the Lorentz invariance is a symmetry, then the new solution must be obtained from the old solution by just doing a change in the coordinate, that are the only things that change. And it might be some change here, but dictated by the Lorentz thing. The only things is we have done a Lorentz transformation. So we want that everything depends just on this transformation, but nothing else. Okay, so if we require that it has the same form, the equation of motion, then it means the solution will be the same. We have only to change x into x prime, and maybe we have to change psi, okay, but in a manner that has to depend only on this form. So covariance means this. This is meaning of covariance. The equation of motion, even in the new variable, have to have the same form. And, you know, we don't want to end up in an equation totally different, of which we have no relation with this one. So we want to end up in an equation that has the same formal structure. And why we want the same formal structure? Because in that manner, the solutions are the same, provided only we change x in x prime. And in fact, for the Klein-Gordon, we only had to change x in x prime. We did not have to change psi. For the Dirac equation, what we will see the difference is, for the Dirac equation, there is a manner to preserve the same form, but we have to change not only x, because that is our, but also psi, but in a manner that depends only on this coefficient. That is the goal of what we will see. Okay? So differently from the Klein-Gordon, the Dirac equation maintains the same form if you change not only x, but also psi, but in a form that depends only on this. These are the only ingredient. Okay? So that is what we will show. Okay, now first of all, let's look how the gamma mu change. Now, we know that the gamma mu have to have this anti-commutation relation, the one that we did before. And this relation must hold also in the prime frame. This is the prime frame. Gamma mu prime nu plus gamma prime mu is equal to what? This does not change under a prime. This is a tensor that is diagonal, 1 minus 1 minus 1 minus 1, and this is like the vector that gives us the 4 length, so it does not change. Remember that this is only the object that lower and raise the indices, and G mu nu was 1 minus 1 minus 1 minus 1. Why it remained the same? Well, remember c squared t squared minus x squared minus y squared minus z squared is equal to c squared t prime squared minus x prime squared minus epsilon squared. You know, here, this object is nothing else than x mu, g mu nu, x nu, and this object is x prime mu, g mu nu, x prime nu. Okay? And you see, this is what makes my 1 minus 1 minus 1 minus 1. Here I have the same sign, so it remains the same. There is another manner to that I'm trying to see what I wrote down here a few days ago. Okay, the Hermitian property of the gamma we already did. The gamma 0 is Hermitian, and the gamma I are anti-Hermitian. Okay. So, okay. Okay, now, so one thing we have done. Now, let's look the third thing. So this is what we get. Let's look at the third things. Let's look at the Hermitian property of the Hamiltonian. Okay. Okay. Yeah, if you know, if you write this equation in the following manner, I h gamma 0 dd psi prime ddt prime equal I h till h d psi prime, this okay, if we use this object as Hamiltonian, I put a tilde because it's not the old one. This one would not be Hermitian because this one would have the gamma I, and the gamma I, remember, are anti-Hermitian. So the H tilde D is different from the one that we had. It was we have to multiply this by gamma 0 in order to get the usual Dirac Hamiltonian that was Hermitian. And this one is Hermitian because this one contains the gamma I and the gamma 0. The gamma I are anti-Hermitian, but when you do the dagger, they exchange. You have to exchange gamma 0 with gamma I, and so you lose, because of the anti-commutation relation, you get a minus sign. So this object is Hermitian, while this other object is not Hermitian. Okay. Now, another important piece of information that we need is the following. There is a theorem due to Pauli that says the following. Is a theorem that is proved in the book as an exercise, but we will not do. It's a very long exercise. That if you have four matrices that satisfy this relation, any set of matrices that satisfy this relation, the Pauli theorem tells us that choose any gamma matrix that satisfy this, then they are related by a unitary transformation. That means any gamma matrix that satisfy this, so let's call this prime, let's suppose these are the prime new gamma that satisfy the same relation as the original gamma. They are related by a unitary transformation, where u dagger is equal to u to the minus 1. So the theorem, the Pauli theorem said whatever are the four matrices that you, the gamma matrices are related by the things. Now, we know that this, we said, look, this, when we do a Lorentz transformation, we end up in this with the same things. Of course, the Lorentz transformation then does not change the hermeticity property of the gamma, because if it changed the hermeticity property of the gamma, it would change the hermeticity property of the Hamiltonian. So, in doing a Lorentz transformation, we are just implementing Pauli theorem. And so, this one and this one are related by a unitary transformation, according to Pauli theorem. But if it is a unitary transformation, the physics does not change. So here we can use the same. That means this one and this one are related by a unitary transformation because of the Pauli theorem. But the unitary transformation does not change the physics. We know that, okay? So we can use the same. So basically, if you want to write this, for example, in the following manner, this plus prime minus m0 psi prime x prime, remember that this p prime is just p mu gamma mu with the old gamma mu. Okay, so this is the equation. We know that the x will change. Now, I insist in having an equation of this form. This we will see that we can achieve only if we change the psi in a particular manner. So the covariance is something we impose. I want that it maintain the same form. I have seen that the gamma I can take the same gamma, but the x I have to change. Now, to keep the same form, we will see that the psi, the form of the psi has to change, but I want that it change in a form that depends only on the Pauli matrices, okay? So, basically, psi prime x prime, that is psi prime a mu nu of x, I want that this object is nothing else than some matrix working in the Hilbert space psi of x. So you see that I have gone back to the old form of psi. I have gone back to the old x, but I say, listen, this object, I want that it has this form. Now, it's not that I want, that is the only manner. And now we will find out how S is. This is the only manner to have the same form of these things. Now, the other things that we will require is that S can do only linear combination of the psi. Why? Because after all, even if relativistic, we are doing quantum mechanics, and we know that in a Hilbert space we are allowed only to do linear combination. We can sum and subtract with some coefficient. wave function, nothing more. Okay. Okay. Now let's see if I can, this one you can write also in this manner, SA, and let's put a hat on it because it's an operator, and then psi I want to write as a function of the x prime, then it means a to the minus 1 on x prime. Okay, so if I want to write this as a function of x prime, this is the relation. And it's easy to see that there is an inverse of this relation that I wrote down here. There is an inverse. I want also that there is an inverse, because if I change my psi in this manner, I want to be able to do the other way around, and the inverse is this. That means I want to be able to go from psi of x to psi prime of x prime, and I call this s to the minus 1a. Okay. And how you can derive these things? You can derive, okay, so we want this to hold. Now in this relation, let's change x into minus x. So in this relation, let's send x into x prime into x, and psi into psi prime. Then if you do that, you get the following relation. Psi of x is equal to psi a minus 1 of x prime s a to the minus 1 psi prime x prime. So I take this and exchange x in x prime in x, and psi in psi prime. I get this relation. But now let's compare the two. If we compare the two, we derive immediately that s to the minus 1 of a is equal to s to the a to the minus 1. Another feature of this. So this matrix that we have not found yet, that change the wave function, is linear. We impose it that is linear, and we discover it has this property that when it depends, it is built in a complicated manner, we will see, out of the a, but it has this nice property that the inverse of this function is equal to the same function or to the same matrix of a to the minus 1. Okay, so these are all the features that we want out of this matrix S. It might be that we work all this out and find out that the matrix S is the identity, like in the Klein-Gordon. In the Klein-Gordon, we had only to change the argument. The wave function never changed, okay? Remember, it was a scalar. In that case, we say it was a scalar. It did not change. Okay. Now, let's use this equation now. Let's use this equation. Let's in particular use this one. Let's use this one into the Dirac equation. So let me cancel for the moment. Let me cancel this. Okay, let's rewrite here. Okay, and let's use this relation. Let's now use this relation. Then we get I h bar gamma mu d dx mu minus m0 c s minus 1a psi prime x prime equals 0. This means I, H, gamma mu. S is a matrix or is an operator in Hilbert space, so it does not see these things. It can pass through, okay? Means it changed the things of this wave function, so we can write it in this manner. S minus 1a d dx mu minus m0 c s to the minus 1a, all these applied on psi prime x prime equal 0. Now let's take this equation and let's multiply by on the left by SA. Let's multiply this on the left by SA. Then what do we get? We get, let's write it here, we get I H bar SA gamma mu S minus 1a, then d dx mu minus m0 c psi prime x prime applied on psi prime x prime equals 0. So I have taken this object and used this relation, replacing this by this quantity. We made this pass through, but we did not pass it through the gamma mu, okay? And we will see why it cannot pass through the gamma mu. This S acts on the component of psi, but gamma mu also acts on the component of psi. So this is a matrix in the component space of S, of psi, okay? So this is a matrix in the component space of psi, so it cannot commute with gamma mu because also these act on the component. It might, but in principle, we better not accept that it commute from the beginning. We will see at the end how it goes. Now that we have got this equation, let's, the variable here are x prime, so let's change variable. And from this one, let's go to the new coordinate. You know, if you change variables, so let me now start canceling, otherwise I cannot do anything anymore. So let's change variable here. I want that this derivative goes into a derivative with respect to x prime, but we know that the transformation is d dx mu is equal dx prime mu dx mu d dx prime mu, and this is equal to a mu mu d dx mu. Okay. Then the Dirac equation, now I replace this with this expression, so I get I h bar s a gamma mu s to the minus 1 a mu mu, derivative with respect to x nu minus m0 c, all these apply to psi prime x prime equals 0. Now remember that all these transformations that we have got here are only due to the transformation of the x, are only due to the form of the S that I have to find, but I have supposed that it acts in this manner, as we have seen here. And now this one has to be the old Dirac equation in the new variable, but we made the hypothesis that in the old variable, the new Dirac equation should be this, IH gamma mu d dx prime mu minus m0 c on psi prime of x prime equals 0. That was our hypothesis, right? Our hypothesis was that the gamma mu don't change because of the Pauli theorem, they are unitary equivalent anytime they satisfy those relations. So we want that this is that equation. That means we want that the Dirac equation does not change in form, and it has this form. Then for that to happen, you have to have that this quantity here, should be the gamma mu. So if you want that this object, this equation, is like that equation over there, then you need that S A gamma mu S to the minus A, and then, sorry, A mu is equal to gamma nu. Now we use the orthogonality relation of the mu that we had wrote before. You remember A mu nu times A mu is equal G mu nu. So if you use the orthonormality relation, you get that S A gamma mu S to the minus 1A is equal to A mu nu gamma mu. So this is the relation that the S, that is the one that rearranges the component of the psi, has to satisfy. So let's write down here S, where is it? SA gamma mu S to the minus 1A is equal A mu nu gamma mu. Okay. So from here we went to this one. Now that is what characterizes S, but then we have to find the form of S. So I want to be clear to what is happening. We want that the Dirac equation does not change form, so this is the form in the new things. We have allowed anyhow psi to change form, in the sense to rearrange its component according to some matrix S that is linear matrix, and it can at most rearrange the component, and it must rearrange in a manner that depends only on the mu nu. That is the only things we allowed. We have been, I mean, you can say, why did you allow that? Well, if that is the requirement, that rearrange only the component of psi in a manner that depends on A, once you give me A, I can derive everything, okay? And especially having this, the same form as the original Dirac equation, the solution will be the same. I can take the solution from the original Dirac equation, replace x with x prime, and replace psi with psi prime. That is only a rearrangement of the things. So now the next things that we have to do is to find the solution of this equation. So we have to find a solution for this, okay? Means in that manner we will find the explicit form of S. It will take us the next 5 minutes, and then most of the time tomorrow. It might be that as solution we get the identity, but if we had done a similar treatment for the Klein-Gordon, we would have got as S the identity, just because the gamma don't exist and so on and so forth. So S rearranged the components, the 4 components of psi. So S of A has to be matrices that are 4 by 4, but still they could be the identity. And of course, let's start solving that equation for an infinitesimal transformation. So let's suppose we have an infinitesimal transformation. That means delta mu nu times delta omega mu nu. Okay, an infinitesimal one. So an infinitesimal one for the Lorentz transformation is the identity plus some small things. We can lower and raise this index, and then we can say, listen, this one will be something like this. Delta omega mu nu, this is the identity, so it's the same. So S is effectively a function of this quantity. And as it is infinitesimal, we can expand in it. So when it is zero, of course, we want that this is the identity, because if we don't do any Lorentz transformation, we don't change the psi. If we don't change the psi, it means this is the identity. And then as this is small, there will be a first term, and let's call that term delta omega mu nu. And then this is a matrix 4 by 4, this is a matrix 4 by 4. In front here, we put a matrix 4 by 4, and we indicate it in this manner. We don't know this sigma yet, but this for sure is the form that this S will have for an infinitesimal transformation. The identity, and you can say, why did you put minus? It's just a convention. Okay, I could have put plus. The parameter, that is and this parameter is related to the Lorentz transformation plus some matrices. Now, these are not, this is a 4 by 4 matrix, but not in the index mu nu. The index mu nu are the index of the transformation, okay, of this parameter. So these mu and nu can go from 0 to 3, okay, but this sigma, even if I did not put any index, suppose I don't put any index, suppose this parameter I take just, for example, the rotation along z. Imagine that for Lorentz I take the rotation along z, then there is just one parameter. Even if there is one parameter, this is still a 4 by 4 matrix. Then it means this is 4 by 4 matrix, and how many I have? How many are as the indices? So if these indices were 8, we know they are 4, but they are 8, still this would be 8 times 8, 64 4 by 4 matrices. So the number of matrices, so mu and nu tell me how many matrices I have, and each matrix is 4 by 4. Now, the inverse, if you remember, there was that property that S to the minus 1 of A is S to the A minus 1. So if I take the inverse S minus 1 of delta omega mu nu, what do I get? I have only to change this. So I get 1 plus 1/4 sigma mu nu delta mu nu. So here I just want this to be explicit. Sigma mu nu are 4 by 4 matrices, and their number is equal to the product of the number of nu and the number of mu. Okay? So sigma, even if there is no index here, it would be a 4 by 4 matrix. Then how many 4 by 4 matrices I have? As many as the mu and nu. This is very crucial because very often people do mistake and think that these mu nu are index of sigma. So actually we should put a parenthesis to indicate that they are not index of sigma, they are not index of their elements. Now, remember the delta mu nu are antisymmetric. If you take a Lorentz transformation, this is antisymmetric. It's not difficult to see. Let's see if we can do it. No, there is no time. Then the sigma mu nu must also be antisymmetric, otherwise the S matrix would be 0. So this is antisymmetric. Not as matrix, antisymmetric in mu and nu. Okay. Now, why? Let's make the proof of why they are antisymmetric. They are antisymmetric because this is antisymmetric. Why? Okay, let's start. Mu nu is delta mu nu plus delta omega nu mu. Okay, now we know that for the orthonormality relation, mu nu and mu sigma is equal to delta sigma mu. So let's insert these. We have delta mu nu plus delta omega mu nu, delta sigma mu plus delta omega mu sigma, and this is equal roughly, let's neglect the second order because it is infinitesimal. This is delta mu nu, delta sigma mu plus delta mu nu, delta mu sigma nu plus delta mu sigma delta omega mu nu, and we neglect the second order things. This is equal to delta sigma nu plus delta omega mu sigma delta omega sigma nu plus. But you see, this object is equal to this, so these things must be 0. This tells you that the omega have to be antisymmetric. Okay, so from the orthogonality relation of the A, and these come from the invariance of the length, we get that the omega AB have to be antisymmetric. If these are antisymmetric, also these are antisymmetric. Not as metrics. They are not antisymmetric as metrics. They are antisymmetric in these two indexes. And these two indexes, as I wrote down there, are not matrix index. These are indexes that label which matrix I am using. Okay? This is, I insist on this because it's a very important point. Now, tomorrow what we will do is we will solve this equation and found the form of the S. Okay, and we will see they are not the identity, differently than in the Klein-Gordon. Okay.